keep it real with it most. Marcy,
Hi, I'm Juha and I'm a hockey player here at USC. I will be going through some physics concepts and examples with you this semester. And remember, just like on the ice, there's no such thing as luck in physics. Just keep your head up and work hard. In 1687, Isaac Newton published his law of gravitation in his famous book Principia. And the law that he stated says that there is a gravitational force between any two masses in such a way that the force is proportional to the product of the both masses and inversely proportional to the square of the distance between them. And then there is some constant g, a proportionality constant in short, whose value was still undetermined. And where did he get this relationship that is inversely proportional to r squared? We'll get back to it later in the following videos when we talk more about celestial mechanics. But why this result was so important was that it explained the movement of planets, and the law of gravitation as we see it here was also seen to hold true at any given size scale in the universe known at that time. And of course the question remained, what is the value of G? And about 100 years later, a person called Henry Cavendish set out on a mission to determine the value of this mystical constant. And this is what he did. Here is an illustration of his experiment. So in short, he had heavy masses, the big balls, that were placed next to small masses, and they were hung from a quartz fiber. So according to Newton's law, the big and small masses, they attract each other, which in fact, or in turn, makes the quartz fiber turn. And by measuring how much the fiber turned, he was able to deduce the amount of force. So in effect, the Fg on the left-hand side. And that was based on knowing the torsional constant of the quartz fiber that could be determined by other means. This was a very delicate measurement, so the scale of the force that he was measuring at the time in the late 1700s was about 10⁻⁷ newtons. So that was a remarkable achievement on its own. But now, when he was able to measure the force, we know the masses m1 and m2, the big and the small balls, and also the distance between them. And from those results, he was able to establish a value for G. And he got pretty close to the value that is recorded nowadays. So 6.67 times 10 to the minus, not 24, that's 11 Newton meters squared per kg squared. And this is known as the universal constant of gravitation, and it's known to hold everywhere in the universe as far as we know so far. There's also another interesting result that resulted from this experiment. If we take into play Newton's second law, which was also published in the same book, the Principia, and as you know, the second law says this, the net force on an object is mass times its acceleration. And or A in general. And now, if we apply what we know about gravity and falling objects, we get the following. So we know, first of all, that the gravity is, as Newton postulated, g times the mass is involved. So let's say an apple is falling on Earth. It didn't fall on Newton's head, by the way. We can say the mass 1 to be that of the apple, and the other object is of course Earth. And the distance between them, which is the distance between the center of the Earth and the center of the apple, that was about the radius of the Earth, which was already known at that time. So that's the net force, and the mass of the apple, and what is its acceleration as it falls. That was also known to be g, 9.8 meters per second squared. So from this equation, the masses cancel. And if we arrange this, we get me to be g times r squared divided by the capital G. In fact, when Henry Cavendish was doing his experiment, he didn't call it determination of universal constant of gravitation, but he called it weighing the Earth. And the result that he got was about 6 times 10 to the 24 kilograms, which is also pretty close to the established value of today. And let's go back once more. So if you look at this equation, what we have on the left, we can also get the acceleration of gravity if we like. So what we are saying here is that G equals the capital G times mass of the Earth divided by r squared. So this is the gravitational acceleration on Earth. And as the gravitational forces are usually negligible between everyday objects, we tend to talk about celestial mechanics, and we'll continue on that track. So let's compare the gravitational acceleration on the Moon and on the Earth. So what do we get from here? So we are saying that gravitational acceleration on the Moon divided by that on the Earth, we want to calculate its magnitude, in other words. So we get g times mass of the Moon divided by radius of the Moon squared divided by, same thing for Earth, g times me divided by radius of the Earth squared. So those g's cancel, and we get mass of the Moon divided by mass of the Earth times radius of the Earth divided by radius of the Moon, and that whole thing squared. From experience, or at least from the experience of the Apollo astronauts who walked on the Moon, we know that the gravity on Moon is about 1/6 of that of the Earth. And we should note that the mass of the Moon is only about 1/80th of mass of the Earth. But because the radius of the Moon is so much smaller, in essence we are closer to the, or if you are on the Moon, you are closer to the center of the Moon. Hence the gravitational force is stronger, and that scales as the second power. That results from this inverse square law. So if that factor is 180, this factor is about 3.67 squared, because that's the ratio of the radii of these two objects. And that fact brings the gravity to a higher value than you would expect just based on the mass of the Moon itself. There's one more thing to note about the inverse square dependence. Let's say we have planet Earth here. Concentration of mass in a spherical shape. And a person is standing on the top. And as long as this person is not within the mass itself, it turns out that the whole Earth can be modeled in the calculations as if all of its mass would have been concentrated in a single point at the center of the mass. And that is the reason why we can only need to consider the distance to the center of the mass. And this is a nice simplification when we don't have to consider the distance of this person to all the points of the Earth separately. We can just make this assumption that all of the mass is indeed in the center of the object in consideration. And that follows from the inverse square nature of the gravitational law. If this power would have been different, we wouldn't have this kind of behavior. But if you will, in this case, we were lucky. Feel the high that you get from the line. If you feel it, raise your hell in the sky. Feel the crash at the top of